Thank you so much for having me. Every time coming back here is like a homecoming because actually my grandma lives 2 stops away in Jinmei. I'm very happy to be here to give a talk and share the sciences I've been working on since the past few years. And this talk especially really highlights my career as a faculty member. Ever since graduating from Northwestern University in 2022, I did like Chen graciously mentioned, I did a 1-year postdoc at NASA Goddard Space Flight Center. And that point really is the transition of my research career from the narrow sort of the climate modeling aspect of my work into something more expansive, hopefully. And that is ultimately my goal, to address exoplanets from birth to maturity. And I'd like to first thank my collaborators, Dr. Lee, Dr. Lasieger, Dr. Kamachek, and Clement, and Evelyn. These are scientists located in various parts of the globe, and they've helped me tremendously as I navigate my career as a junior faculty member, and many of them are in various stages of their careers in different roles. And I would like to thank them for their contributions to my work today. So my work in today's talk can be really summarized by 3 bullet points. And these are the 3 topics we're going to be covering. And like I mentioned in the very beginning, my vision for my research, and hopefully in the near future a research group, is to uncover the chemistry climate dynamics of exoplanets, from rocky planets to gaseous planets, from the early stages of planet formation all the way up to the maturity, the late stages of planet formation. So the first question that we're going to be thinking about is, how can other systems, such as M-dwarfs, systems where you have a very different formation environment, how can no system give rise to essential ingredients such as water and nitrogen and carbon dioxide, things like that? This is a question that we really don't have an answer to, because most of the models who look at these compact systems, these are systems around M-dwarfs, so they're essentially much narrower in terms of the radial extent and their mass. Most of them just assume a disk formation stage, and then once you have a composition gradient, assign each of the planet with a particular composition. You kind of explore a grid of reasonable parameters from that point. And to me, that's not sufficient. If you think about how Earth attained its key ingredients, it's not a simple assignment of compositions, right? It's a whole sporadic process. And these processes includes the scattering of important asteroids and comets from the outer reaches of the solar system beyond the snow line, where you have a lot more things such as water, such as carbon dioxide, such as nitrogen. And as the gas giant grows, this particular Jupiter, as it grew, it migrates slightly back and forth. This is called a Grant Pak paradigm. And during this process, it is thought that the water-rich planetesimals on the outer regions of the solar system get scattered inward to the inner terrestrial planets. This is believed to, this theory is believed to be how Earth has obtained much of its water, or else it would have remained dry for most of the evolution, and we wouldn't have the water we have today. And indeed, we have measured a variety of different asteroids through Rosetta mission and various other missions, and found that indeed some of the carbonaceous chondrites and enstatite chondrites contain essential ingredients such as not just the volatile ingredients, but including organics that are essential for seeding worlds like Earth with life. But the question is, how do these processes operate on a different environment when you're thinking about a compact disk on the left-hand side and an extended disk, probably more like what you find for solar system analogs? There are a variety of different physical and potentially chemical differences that will result from this simple kind of geometrical change, right? And you would imagine that from this simple physical difference, there may be a lot of other sort of implications for it. Here's a fun analogy. On the left-hand side, you have a solar system analog where everyone is living in their own corridor, they're not bothering anyone. So the evolution of the individual planet does not really affect the neighbor. You know, on the other hand, you have a compact system, the subject of our study, where you have everyone crammed in the same space, and whatever happens to the star, if the star changes luminosity, if the star flares, if the environment changes, everyone will be affected at the same time. So this is crucially, this is very crucial because this implies new physics that we need to consider during the process of planet formation. So this is the stage where you have the gas disk, and part of the rocky material has already condensed out from that disk. And then you're thinking about how these planets interact as they start to form. There are two important distinctions from the type of M-dwarf compact environments versus solar analogs. And the two main ones I can think of are the absence of gas giants. You wouldn't find substantial enough gas to accrete, to allow the accretion of eventual gas giants for many of these lower mass disks. And it's also more compact. So the physical implication is reduced radial mixing, probably, because you don't have that migration or gravitational perturbation effects you would find on a solar system analog. There's also the fact that there's less material, therefore maybe increased impact velocity due to the fact that it's more condensed. The lower material may suggest that there's less water or less carbon available to be accreted onto the planet overall. So these are implications that we need to explore. And how do we explore it is very critical, because we cannot just assume that these things are added upon without any type of loss process. And indeed, many of these studies include this study that I mentioned from Raymond et al. In 2011. The way they calculated accretion is essentially just assuming a planetesimal, maybe an embryo, and then add in all the different amount of carbon or water content as the planet grows. The important thing is that we do need to incorporate not just the in-body simulations, which is what people have done, creating planets from the ground up, from the disk to planet formation, planetesimals, and then to the embryos, and then some planets end up with atmospheres as they grow. But you also need to include a variety of different loss processes involved in planet formation. So we need a volatile growth model that tracks delivery and loss for every impact. Every impact could either have a net loss or net growth effect, if you really think about it. And the key physics that are involved in these variety of different processes are illustrated in this cartoon. You have impact loss and delivery depending on the impact velocity, depending on the mass of the impactor. You could get either net loss or net delivery, like I mentioned, or you can have the effects of the atmosphere and mantle exchange come into play. So this is when the mantle can absorb much of the gaseous reservoir coming in, and you may not have enough atmosphere at the end. You may rely on secondary outgassing to increase the amount of atmosphere at the end of planet formation. So these are important processes that need to be included in the more complete consideration of what the final volatile content of these planets may look like.
So can I ask a quick question?
Yes.
So do you mean there are less volatiles in the M-dwarf disk environments available for forming planets, or are there intrinsically less volatiles in their disks?
It's something that we don't have a direct observation of that. What we did is we assume a kind of a range of initial starting amount of the volatiles. So maybe some of them has a solar analog, and we let it evolve over time to let the loss and the growth process come into play. But the initial disk composition, which is probably what your question is, that one we don't have a good constraint of. We have a little bit of constraint based on disk measurements, but not to the extent that we hope it to. So we assume a disk profile and a few reasonable composition as the initial disk composition. So one thing we apply our model, one system that we apply our models to is a TRAPPIST-1. Many of you might have heard of this system, it's a very famous one. And it is a good test bed for many of our theory as to, do these planets have an atmosphere? Do these planets have water? And this is a timely study, I think, because we're just now able to use JWST to look at the atmosphere through transit transmission spectroscopy, looking at which of these planets actually has an atmosphere. We've measured B, C, and D, and turns out the planets B and C are somewhat conclusive that they don't have an atmosphere. D is wishy-washy, right? Is that correct? We're not sure about D, and then the rest of the planets are to be determined. So D and E sits in a place where we're not quite sure what is the interpretation for those planets. Here's our result, which is showing here is a few select examples. This is the result for planet B, which is the innermost planet. This is a scorched world in the sense that it's very hot. We expect the equilibrium temperature to be very high because it's sitting at 0.01 astronomical units. You can see the growth of the atmospheric water and the mantle water in this plot. And we find that for this planet, as the planet increases its mass, much of the water throughout the bulk of the planet remains quite low. So we conclude that this planet has a barren surface and a dry interior. For the next planet, we can think about planet C. Surprisingly, if you look at the evolution of the atmospheric water, we find that it end up with about half for most of the simulation, for the median simulation. We find that it has about half of the ocean mass in its final atmospheric reservoir. This is surprisingly more than what we expect. And the fact that we don't see any water in planet C might suggest that if it was formed wet, but then much of the water was lost subsequently through photoevaporation. But we do find that most of the simulations result in a substantial fraction of water in its atmosphere. So for TRAPPIST-E, this is where I think is very interesting. For TRAPPIST-1E, many of our simulations finds that it can end up with a few times of Earth's water. We're just showing water now. I have results for carbon dioxide and nitrogen. And this means that TRAPPIST-1E could have much more water than the entirety of the Earth's ocean reservoir and holds promise for future observations. The fact that the most recent JWST observations of TRAPPIST-1E finds an inconclusive sort of evidence for whether it has an atmosphere or not is very interesting, because that tells you that even if the planet has formed with a lot of water, much of the post-formation process may have further sculpted the initial inventory of the water. And we can look at the bulk kind of statistical number of occurrence of different planetary volatile content amounts. Initially, you can look at planet B and C. This is consistent with the fact that most of the planets are in red, in the sense that they're quite dry. This is a separation of dry and wet population between red and blue. For planets D, E, G, and H, we find that many of the planets end up with a lot of water. And these is consistent with the fact that they are further out, therefore they can retain more water as opposed to the inner planets. We can also look at a more holistic view thinking about how the final compositions, the final mass and compositions of a variety of these planets compare with the observations of the real planets, which is shown as the open circle, B, C, D, E, F, G, and H, and then compare that with the young planets at 50% assembly and 100% assembly on the right. So we can see that much of the predictions for B, C, and D are relatively dry. And planets E are interesting if you think about young TRAPPIST-1 analogs. They may be, some of them may be dry, some of them may have a little bit of water, and so do the mature planets. So you can see that the bulk of the finding is consistent with the observations for planets B, C, and D, but the outer planets are to be determined for future observations to assess whether if our prediction with regards to the amount of water and many other gases that we have calculated in our model is whether those predictions are correct or consistent with observations. So what can we conclude from just looking at the water? And now I want to move to the mature planets. As a planet matures, what happens to these TRAPPIST-1 systems? But before I do that, I do want to talk about a few conclusions. So as the planet evolves, once it forms with the given amount of water that we have assigned it to, in our planet formation simulations, what happens? Well, it's going to evolve. It's going to lead to climate evolution. And we predict that for the inner planets, many of the planets, including D and potentially E, could lead to greenhouse climates. The ones more akin to the climate you find on Venus. For B and C, they're just going to be barren, just like Mercury. And you can see that for the outer planets, they remind you of Earth, and perhaps maybe not Mars, but Titan. Titan has a very foreign sort of environment. You would find that planets F, G, and H may be Titan-like planets. And planet E sits at the margin. It could be either Venus-like or Earth-like, or potentially having a very different surface atmospheric chemistry than what we're used to, if it's much more different than the other planets. So this result was very excitingly featured on CNN a couple of months ago when a CNN reporter saw my paper and reached out to me, and they were able to put this study into the context of some of the recent JWST observations of TRAPPIST-1, D, and E. And I made a few sentences of comment as to why I think these observations are really exciting and somewhat consistent to what we predicted. There are a lot of caveats I skipped over with regards to modeling techniques and the detailed physics, because this is only, again, one of the three topics I want to discuss today. We have plans to improve the model further and refine our predictions in order to better predict or inform and interpret the data from current and future instruments. Right, so the next topic I want to talk about is what happens when the planet has finished forming. Now, there are a few ways to go about this. Once a planet has finished forming, you can start something called an interior evolution model. This is a widely employed method in current literature with a variety of exoplanet scientists. Assign some kind of interior composition, let the planet evolve through the interaction with the core and interaction with the atmosphere. And we find that our results can actually help these interior models. If they use our mantle or shallow mantle composition and help them evolve their interior model, I think that's going to increase the model realism. The other sort of directions where I'm kind of, I would say, more experienced in, so it's a direction I'm planning to take, which is looking at once the planet has formed, looking at the spin-orbit dynamics particularly the spin orbit dynamics and their effects on the climate over the time scale of billions of years, right? Earlier, we were thinking about the time scale of 0.1 to up to a few million years. This is up to a few, this is a much larger time scale of climate evolution. And this is, much of this effect are inspired by what we've seen on Earth. So Earth has experienced changes in its orbits, changes in its orbital parameters that have led to ice house climates, greenhouse climates, and a variety of variations in surface temperature. And these effects might be even more amplified in compact multi-planet systems such as TRAPPIST-1. We're influenced primarily by Jupiter. However, if you have a planet right next to it, these are, the whole system of TRAPPIST-1 fits inside the orbit of Mercury. So if you have a variety of planets next door to you, such planet-planet perturbation may be important. And here's a cartoon illustrating this effect. I spent hours drawing this cartoon, even though it looks kind of crude. So previous study, and this is by Dongjie Li's student, not me, Chen et al. Paper, found that if you just employ a series of n-body integrators, they find that the mutual interactions between planet to planet can actually overcome or compete against the tidal forces from the host star. So you'd expect, in majority of the cases, these are planets that orbit within the tidal radius, the tidal locking radius. So you would expect all these planets to be tidally locked, but they find that actually may not be true. It can lead to libration of the substellar point. The substellar point, the hemisphere facing the host star, may not be entirely aligned due to the effects of planet-planet perturbation. And we were inspired by the study, and these studies were inspired by the Earth. We were trying to think about how these fluctuations in the spin-orbit evolution pathways can affect the climate states of these planets. That's ultimately where I started off studying exoplanets when I did my PhD. So I'm excited to test this theory because much of my simulations in the past have used static orbital settings. We just don't evolve anything. We just set the liquidity and the eccentricity to a fixed value. So we used the GRIP package. This is the same model that Adeline has used for Monday talk. And we used this model to figure out how, figure out how the evolution of the planet's spin and orbit parameters can affect the climate of the planet. And because we're integrating this planet for thousands of years, we decided to use a less complex Earth system model. Most of the climate models that I've been using for my PhD and some of my research requires months of integration time on a supercomputer in order for it to get to steady state. We can't afford taking years to run a simulation, so we decided to use a less complex Earth system model. It's still a three-dimensional model, but requires less time and less effort to run a simulation. We're just seeing how the climate evolution can be affected by the spin-orbit coupling of these planets. And we eventually plan to use a spectrum generator, the planetary spectrum generator, to allow our predictions of the planet and the atmospheric composition to reflect in the planet's spectrum. So we've done a little bit of this, but I don't have results for this yet, but one day we will. So this is to be announced. We find that the substellar longitude, which is the longitude of the planet facing the host star at 180 degrees, can actually change over time. And this is for TRAPPIST-1e. Most of it sits quite close to the 180, right? And it fluctuates drastically at the end of our simulation. This is, by the way, this is a slice of the end of our simulation. In the beginning, it's pretty much the same. So we just took a 400-year slice. For TRAPPIST-1 B, C, D, it doesn't have an effect. It's pretty much aligned with the 180 point. So TRAPPIST-1, the inner planets for TRAPPIST-1 are very much affected by the tidal alignment effect. Whereas for the outer planets, for planets E, F, and G, and further out, you can see that the gravitational interactions between the planet has allowed the planet to deviate substantially from the 180 fixed substellar longitude assumption, right? And what are the effects of this deviation onto the climate? First, we can think about sea ice. So you can see from this graph, this is the evolution of sea ice thickness. We know on Earth that sea ice is very important for life and habitability. So this is one of the main metrics that we're thinking about in terms of thinking about planetary habitability. It doesn't seem to have much of an effect. The only thing here is changing the atmospheric composition. You're just warming the planet, so it makes sense that you have less sea ice. But it seems like the orbital effects are not significant, right? So it doesn't deviate much from the synchronized, which is the black curve. Not much difference. You can kind of approximate the climate of the control with the synchronized. Not much would be lost for your prediction. Now, what about for planet F? You want to guess if it's a large effect or a very small effect? The small effect wouldn't be here, right? So the effect is quite large, and even changing the solar spectrum, we find that it can rapidly allow the planet to be completely frozen. So what does this mean if we're trying to look for biosignatures and habitability signatures for these planets? This means that if the planet is not tidally locked, if it experiences strong planet-planet perturbation, it would more likely be completely frozen or be locked in a frozen state rather than be having some kind of open water in its substellar point, which is what we'd expect for these eyeball planets. So drier glowing atmospheres causes rapid glaciation. And the next step is to include not just the fact that the substellar longitude changes, but obliquity variations. So that first study, we're looking at substellar longitude variations. What about the changes in its obliquity? Now, this is very interesting because if you force changes in its obliquity, you can get a much more increased climate effect, but also a photochemical effect. So that is the part where I'd like to leave you after this slide to think about the evolution of the obliquity, the axial tilt, and how that may affect not just climate, but photochemistry. All right, so this is very preliminary work that's been done by Dr. Lee and I. She's at Georgia Tech, and we're trying to figure out, by changing the tidal parameters, the love numbers, see how that can affect, just playing around with it within reasonable values, see how we can allow the obliquity to change over time. So this is for the love number 0.1 and tidal quality factor 0.8. This is for one set of specific simulation. We find that the obliquity, we can drive the obliquity to very extreme extents. So this is probably not that physical. We're trying to test out extreme values. In some of the cases, we find the below certain threshold rigidity, the obliquity can be driven to a very large extent. The bottom is in thousands of years, so 80,000 years is our total integration time. There are also cases in which at higher K2, instead of being a chaotic regime, you have a somewhat stable, but marginally stable regime where the variation in obliquity follows a quasi-periodic trajectory for only tens of degrees of amplitude variation. This is probably more realistic to what we're going to be seeing, because you might get a higher rigidity for some of these cases. Now, when you put it into thinking about it from an observational perspective as to what the implications of these results are. So this is not a published result. The earlier paper was a published result. This is still an exploratory study. And if you're thinking about observations and you think about the variations in obliquity, we can easily, well not easily, we can sort of do a proof of concept study and put these profiles in its variation to a chemistry climate model. We ran a few years of the chemistry climate models to see how we're going to be able to assess whether if this planet is indeed experiencing spin-orbit coupling, or whether if it's just a stable planet around a host star, like what people have assumed. And this is what we found for a few orbits. Now, I should add to the caveat that this is not equilibrium. This is definitely not equilibrium. We haven't read it to the full extent, so this may be completely wrong. But we find that in many of the cases, the ozone column of this planet experiences chaotic spin and increased obliquity variations could have a much more drastic ozone column variation as opposed to a planet with a fixed spin. So this is a planet with a little bit of oxygen, a little bit of nitrogen, and very Earth-like amount of water. If we put that planet next to a multi-planet system where the obliquity variation is driven by the neighboring planets, this is what we're going to see. And if we assume a fixed orbit, we're not going to see these features. It's very important to include these effects if we want to eventually characterize its observable spectra, both in transmission and in emission, and eventually in reflected light spectroscopy. Okay, so now we're on to the probably my most recent work on this subject. So I've been thinking about gaseous planets since I was an undergrad. My first project as an undergrad was on using MESA. Many of you probably have heard of MESA before. Use MESA to think about planet evolution. We adopted a stellar evolution code to work for low-mass exoplanets. And we've come back to this because one of the things that we find interesting for these compact multi-planet systems is if there are gas giants, which for some of the higher mass cases, there might be gas giants, maybe not the TRAPPIST-1-like systems because the mass is so low to begin with. But if you have a gas giant, something interesting happens. So this is a paper published almost 15 years ago now, from Batygin and Stevenson. So they proposed a method to inflate the atmospheres of hot Jupiter. So the fact that hot Jupiters have much more inflated radii is somewhat of a, I wouldn't say a mystery, but an unknown problem that people find difficult to solve despite exploring a variety of different heating mechanisms. So the method that it proposed is called ohmic dissipation. It involves the interaction of the stellar magnetic field and the planetary magnetic field, which drives intense stellar winds that eventually induce strong currents that gets deposited into the deep interior of the planet's envelope, hydrogen-heaving envelope. And because of the resistance within the hydrogen-heaving envelope and the formation of alkali metals, ionized alkali metals, that drives the currents and resistance, that leads to a large energy source and could explain, using first principle physical calculations, they find that it could explain the increased radii of many of these hot Jupiters. So this is a graph showing that case in which you have the radii is shown on the y-axis and the x-axis is showing the equilibrium temperature. We find that something very interesting happens. When the equilibrium temperature exceeds around 1400 Kelvin, you find that these planets are observed and these evolution tracks are modeled. And this is with the ones with error bars are observed planets. We find that as the planet approaches this regime, we find more inflated hot Jupiters. And this 1400 Kelvin threshold is the regime in which alkali metals, such as sodium, starts to get ionized. And this is consistent with the theory that the ionization of these important alkali metals is one of the primary causes of the inflation of Jupiter's that provides in which ohmic heating provides additional heating source. Okay, so what does this have to do with us? Well, we find, where we're just bored, I don't know why we ended up thinking of this study, but we apply this for hot Saturns. So if we look at hot Saturn, if we think about the evolution of hot Saturns as a function of time, we can compare, once we implement the effects of ohmic heating, we can compare a planet without ohmic heating, this is a planet very close to the host star, and another planet without the effects of ohmic heating. We find that the differences are quite drastic. And similarly for the hot Jupiters, we find that for these hot Saturns, the radius could be much greater with the incorporation of ohmic heating versus the dotted case or dashed curves in which there is no ohmic heating. So it's a large radii differences there. And this only occurs when the magnetic Reynolds number exceeds the critical magnetic Reynolds number, which allows the onset of a magnetic dynamo. So this is consistent with the fact that the effect only happens when there's a substantial magnetic field from the planetary interior. We can also look at the mass loss rate. But the mass loss rate is a very preliminary result from Daria and I, who is my grad student. We find that the increase in mass loss rate is actually significant as well. Whereas for hot Jupiters, if you increase the mass loss rate, even for gigayears of time, even when you integrate gigayears of time, it doesn't really affect the bulk mass of the planet because it can lose some mass and still be hundreds, above 250 Earth masses. Whereas most of these hot Saturns only have about between 60 or 100 Earth masses. So changing its mass has a much more sensitive effect on its bulk evolution trajectory. All right, so, and this increase in mass loss rate is what we think a crucial piece to uncover or explain the so-called hot Saturn desert. If you think about how the effects of the ohmic heating is affected by the different masses and the different orbital separations, there is a regime which is around the sub-Saturn, not really the Saturn, but smaller than Saturn, the sub-Saturn regime in which the dipole field is the strongest, the ohmic heating rate is the strongest, and the mass loss rate is also the strongest. So this is all physically consistent simulation. It's changing the mass. The equations for ohmic heating is essentially the same. And this is very interesting. I will come back to this figure if you haven't fully absorbed this one. But if you look at the census of hot Saturns in this particular regime, we do see a missing region between about 0.02 and closer to 0.03 or 0.04 astronomical units. There is a missing region of no planets. This is in a Saturn mass region. And indeed, the region in which these planets correspond to are around the cases for the red curves, where we need to do more simulations. We have only done 3 masses and a few orbital radii, but once we are able to do the full parameter sweep that covers this entirety of extent, we're going to go up to 0.02 astronomical units to map out the full distribution of the planet phase space. We are going to be able to see how our synthetic population compares with the observations shown here. So this is a interesting kind of hint as to this may be the solution for the hot Saturn desert, but it's not entirely conclusive yet, but still work. I just put this together last week, so I'm very excited to present this for the very first time, and hopefully by some of the future conferences in the coming summer and early next year, we're going to be able to fully characterize the entire planetary parameter space. And that, I can leave you with my some of my conclusions, which is that stochastic accretion from the early times of planet formation between 0.1 and 10 million years are very important to determine the final states, final as in when a planet finishes forming, the final states of the small planets, in particular in multi-planet systems, because multi-planet systems has a very different formation environment compared to those in more extended solar analogs. And the other implication is that once these planets have formed, many of these planets would experience strong planet-planet interactions, in particular for multi-planet systems like TRAPPIST-1. And for most of the studies on this effect, they have been neglected these planet-to-planet interaction and just focused on the planet and star interaction, which is insufficient for these tightly packed systems. The final thing, this is sort of a tacked-on project, as you can kind of tell, but this is the thing that my student and I are working on actively. The very last bullet point is that we may be able to use ohmic heating as a potential solution for the hot Saturn desert mystery. So that is my talk. Thank you all very much. I'm excited to have shown you my most recent work. I'm happy to take questions if there are any questions, or I'm happy to answer any questions via email as well. Thank you.
Thank you, Howard, for the amazing talk. Time for questions. So, okay, go ahead.
Yeah, thank you for the talk. Yes. Can you say a little bit about this stochastic accretion? How do you model this starting accretion to set up this initial condition for this post-evolution, post-formation evolution?
So this is something I glossed over because of time restriction, but the setup of this, being the planet formation case, right? The setup of this simulation is really just assuming that once the disk has somewhat dissipated, you're left with a certain initial number of planetesimals. So maybe around on the order of a few thousands, depending on the setup of the simulations. So set a density profile for these different individual planetesimals, and then you start running the simulations. You start allowing them to collide and interact, and some of them may grow to planet embryos, some of them may experience collision and remain very small mass. In fact, Mars is an example in which it has remained a planetary embryo. Some of them has grown to much larger planets because of the limited mass in our simulations. Most of them have grown just up to around 2.5 Earth masses. So this is the upper edge of the growth, right? So the setup is really just determined by the density profile of these materials. So we have smaller masses distributed across the entire disk, and some larger masses to simulate the initial embryos, as you would expect during the condensation of the disk to solid phases. Some of them would be very, very large. As you can see, there's a variety of population here, even as the mass gets condensed out from the disk. Some of them will be very, very small. So we try to capture that full size distribution for the initially condensed out material and allow it to evolve from there.
So it's an in situ giant impact type model, gas-free.
Yeah, I mean it's not it's not necessarily giant impact because it's planetesimal impacts, right? There are giant impact events, sure, but they are pretty sporadic throughout the entire evolution. It's just the interaction between the two, the variety of asteroids. So they're in terms of size, they're a few kilometers initially. The smaller ones are maybe 1 to 2 kilometers, up to series size on the order of hundreds of kilometers. That's kind of the size distribution that we select for the simulation.
This This is super interesting. So many questions, but maybe two questions on top of my head. One is, when you looked into the planet-planet interaction through your evolution, have you included gas giants, or do you assume they are, if giants are present, most small planets will be scattered away?
Yeah, so actually, we can't form any gas giants in our case. So for our, you mean for this study, right?
Yeah.
Yeah, we couldn't form any gas giants. The simulation, I think we have a huge table for all the eventual sizes for the planets. The largest planet is about 3 Earth mass. So you need up to from the core accretion theory, you need up to 10s of Earth mass in order for it to start accreting a lot of the hydrogen helium. So we couldn't find any gas giants. Now, if you change the system, you maybe add more mass to it, or maybe make it slightly extended, you could get gas giants. But again, our simulation is TRAPPIST-1 analog, so it's meant to be very, very small, compact.
Yeah, focus on M-dwarf systems.
Yeah, just very late type M-dwarfs. These are our main focus.
Got it, thanks. Next question is about the how, I think you have a slide where you show your climate evolution for the ice fraction, and you compare your controlled simulations to where you have where you have ice albedo effects. So I'm just wondering how the effect of when your host star is M star and ice becomes much darker, absorbing more stellar radiation. Does the feedback become positive because there's instead of reflection, it's more absorbing? How does it play a role in your planet?
Yeah, so that's a great question. That's precisely the effect that we're seeing. So for the non-yellow curves, those are M-dwarf spectra, right? So because M-dwarf spectrum, the effects of ice and water is that it would absorb more of the incident infrared radiation. So it would generate more heat. It would essentially delay the onset of the effect. Now, for solar spectrum, it's more reflective in many of the cases. So it would essentially increase the ice belt albedo effect. So the spectra actually is quite important. And there is a chance that if you shift the spectra enough, it could delay the planet from freezing. But in our simulations, we only explore 2 different types of spectra. The main, we were just testing this out of curiosity in terms of how early can it extend the global freezing timescale. But the main takeaway of this particular study is that you do need planet-to-planet perturbation effects, or else you're going to get a very different sort of picture of what the planet may look like at the end of the evolution.
What's the unit in time? Is it several hundred years?
Yeah, this is year.
Okay.
I wrote it by hand.
Yeah.
Because the initial axes are very small. So this is that's 400 years, the time chunk within our simulations.
So it doesn't really delay too long. I mean, yeah, hundreds of years are still relatively short compared to the system.
Yeah. Are you talking about
like different spectral types, the non-solar, cooler stars. With cooler stars, the effects of ice will delay your entering the frozen state. Yeah.
So this one we didn't. I think this one takes a lot longer for it to freeze, if it ever freezes, for the synchronized case. But one thing we do need to know is that for people who are not familiar with climate models, is that this climate model does not include a dynamic ocean. So the time scale here, it's actually, it's much shorter, because the shallow ocean responds more quickly to the incident radiation. So if you actually use a fully coupled ocean, it might be millions or billions of years, because these models take a few hours to simulate, and one with a global ocean takes months to simulate. And you need thousands of years for it to fully get into equilibrium. So these are just representative timescales, not real timescales for planets.
And you go first.
So I don't work in exoplanets, so this might be a very stupid question. But as I understand that this atmospheres and other things are typically chaotic systems, so it's difficult to predict for a large amount of time, and it depends on initial conditions and stuff. So how do you simulate for 400 years? I'm very surprised regarding that.
So we simulate much longer than 400 years. This is a snapshot of the simulations that we've done. For our the spin orbit simulations, we've done much longer, tens of thousands of years. We're trying to get up to a few millions of years, right, for the full simulation. And what we've done, you're right that the climate, the 400 is a very small window, right? But climate models are much more expensive to simulate. So what we did was we pick out an era, like if we eyeball an era of strong obliquity change or strong eccentricity change, whatever for the orbital parameter you're interested in, and we just simulate the climate in that window, right? We do want a baseline, so we take a baseline for a lowercase, and then we look at an era in which it goes from a very calm state to a very excited state, and look at a climate just for that window. We are not able to afford to simulate the entire duration for the thousands of years duration that we're doing for the spin orbit simulations. That's a very good question. That's a concern that we had when we thought of a strategy to better find a workaround.
Just another question, what kind of, do you use Navier-Stokes equations and stuff like that?
Yes, for our GCN. So, right, that's correct. So it's a fluid dynamics equations. That's correct.
I also have a question about the solar spectrum.
Okay.
So, except for the albedo, does perturbation also change the chemical abundance of the planet hemisphere?
Yes, it does. It doesn't change the bulk chemical abundance, so it changes the variation of it. So that is a very important point. I kind of glossed over as well due to the number of stuff I had to cover. But the effects of the photochemistry, and this is one of the chemical compounds, and there are a variety of other chemical compounds too. This is driven by the fact that different parts of the planet is affected by the solar spectrum, or stellar spectrum, right? Sometimes it's maybe sometimes in the poles it's directed at the host star. Sometimes it's the equator. So the fact that there is a chaos in terms of, or I guess a large variability as to where exactly is the planet facing the host star can lead to a strong variation, right? Initially for Earth-like planets, it's mostly stable. We have an equator, and then the planet rotates smoothly. So most of the entirety of the planet gets a smooth sort of illumination by the stellar spectrum, whereas this is sort of an uneven illumination. So variation is much more different. Thank you for the question.
I have an annoying question for you. So many of the M stars have flares, as you know. So what's the variation driven by flares compared to orbital dynamics?
Yeah, I mean, that is. Have you done studies? Have you incorporated flares?
Yeah, but only in the 1D model, not yet like your previous 3D studies.
Yeah, so this doesn't have flares. It is an interesting thing to think about whether flares can compete with the signal of the obliquity variation signal. I think that's a very interesting question. The main difference is that the flare-driven effects are going to be more stochastic, more random, right?
Right.
Rather than the more, if the obliquity is for just one sort of orbital phase, unless it changes a lot during the few orbital phases. Within that few orbital phase, it's going to look the obliquity signals are going to look somewhat more periodic. So I think that is the main difference. That's a good effect that we will incorporate. I've done a flare paper before, so I've thought about that. But it's just not something we wanted to include here to drown out the noise of the obliquely driven effects.
Yeah, totally makes sense.
Thank you for your question. Yes.
So you mentioned that the 0.04 AU is a point for the sudden.
Yes.
But it maybe depends on the equilibrium temperature. So what is the condition of the host star of this observational
Yes.
simulation?
That's a really good question. I don't exactly know what the sample of the host stars they've taken for this study. I think this is really important. I should have maybe, so this is from another paper.
Oh, yes.
Maybe I should have taken from the archive and just make sure to separate or at least note the dependency on the host star spectra. But that is an important effect, and that could lead to a slight difference into where exactly is this bracketing. But that's something I will compare in the very near future. Thank you for the comment.
All right, with that, let's thank Howard Chen again. Howard and Ellie will be around tomorrow.